This is the second revision video for floating point representation. If you remember from the last video, our final answer was 0.11001 times 2 to the power of 100, and that is how we represented 12.5 in floating point binary. But what if the question asks us to represent these numbers using a fixed number of bits? Let's take that example. So, start it again with the answer. So, step 3 was 0.11001 times 2 to the power of 100. Now remember that was 12.5. If we are representing using a fixed number of bits for the mantissa and the exponent, you have to be careful to put the zeros either to the left or to the right, depending on what part you're representing, or what part you're describing. So mantissa and exponent. Let's make it different. So let's say that the mantissa has to be represented in 16 bits and the exponent has to be represented in 8 bits. So there has to be 8 binary digits for the exponent and 16 binary digits for the mantissa. Now we have the answer there, we just have to make sure that we represent this properly. So think carefully. If we put the zeros, of which there would be 1, 2, 3, 4, 5, an extra 11 zeros on the mantissa, if we put them at the front, multiplying by 2 to the power of 4 will not result in 12.5. So for the mantissa, the zeros go to the right. Okay. For the exponent, if we just keep this mantissa as it is just now, if we add the zeros, the 5 extra zeros for the exponent to the right of the binary number, that wouldn't be 4, it would be 128. So for the exponent, the zeros go to the left of the answer. So if we use 16 bits for the mantissa and 8 bits for the exponent, we would write it as this: 0.11001, and then we have 11 extra zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 2 to the power of the exponent, and we have 5 extra zeros to add in here, so it's 1, 2, 3, 4, 5, and then our original number 100, and that's the answer. And that is how we show floating point representation using a fixed number of bits for the mantissa and a fixed number of bits for the exponent.